as you can see, would be Yu Gao, who's recently joined Texas A&M as a postdoc, and he'll be talking today about dark matter searches looking at the sun and connected galactic nuclei. So please welcome.
Thanks for introduction. So I'm a new postdoc in this fall with Dr. Duda, and in phenomenology, so I find this a very interesting place to do a study on dark matter and also brighter saturated gas searches. And I'm looking forward to that. And today I'm going to tell some of my recent work in the phenomenology related with dark matter searches, especially indirect searches. And as I'm running in this university, and for the last postdoc I was at Oregon, and I graduated from medicine in Wisconsin 3 years ago. And so to physics, we know there's a lot of hints actually for dark matter in our universe, and that we have various experiments looking for them. And these are the satellites or terrestrial labs that's looking for signals coming from outside the Earth. And either they're looking at the high energy charged particles in the cosmic ray, or they're looking at the gammas, or they're actually looking at some very hard to detect neutrinos that can come from either the sun or some other places in the universe, like the galactic center, and which may all, if they have an energy that indicates related to dark matter, could be a signal. And these are some plots that you usually see. There's something missing on the top. It says decay, are the scenarios that where we can search for dark matter. And if dark matter floats around in in our galaxy, they could hit each other and annihilate into particles that we can see. For example, tau plus tau minus or some other particles in the STAR model, and that can radiate. And those are the Fermi's constraints on how large the cross-section will be versus the mass of the dark matter. And very recently, we learned new data from the AMAS-2, which is the alpha magnetic spectrometer for particles. Actually, it's not really started for dark matter, but it turns out they found a lot of excess positrons around the Earth, which cannot be easily explained by known astrophysical sources. So there have been a lot of publication interesting on using dark matters that provide this actual, the actual source for positrons. And what is interesting to know is that we used to have Fermi's measurement on the electron and positrons, which has been there for quite a few years. And recently, the EMS data seems not to agree very well, which is here. You can look at the shape that with Fermi, that actually loosens some of the constraint, especially on the mass of the dark matter, that model builders could try to make to enjoy having more freedom in the way they build the models, but there's some other constraints. I have a few things related to projects going on in this side, which I'm not going to talk today. And what instead I'm going to talk about first is about the neutrinos coming from the dark matter. And in this case, hypothetically, there could be dark matter trapped inside the sun, and if they annihilate, all the particles of the charge will not come out, and the environment gammas will not come out either. And it's only neutrinos can actually penetrate from the very center of the sun to the surface and to us, and could be measured at detectors like the ICE2. So this is a picture of the sun. And if you believe dark matter has interaction with normal matter, they could scatter off the protons or neutrons inside the sun. And if you lose amount of their kinetic energy, it could be gravitationally trapped. And over some time, they will grow in the number at the center of the sun, so their density goes up, they start to annihilate, and then eventually there could be equilibrium. And at that point, you can calculate how much of the dark matter is being trapped and how much annihilate and whether they're equilibrium. So those are some early studies done, I think probably in the 80s or late 80s or 90s, that people have developed the calculation for those equilibrium, but it's only later that we have those beautiful models that does all these calculations. So I'm not going to go into the details of those calculations, but there are a few little things you may want to know that if the dark matter eventually come to a thermal equilibrium with the medium in the sun, their kinetic energy will provide an orbit that is about 1,000th of the solar radius. So they all come from a very small central region on the sun. And that's a good point actually for neutrino calculations, because you know exactly what is the path it goes through and what medium it went through. And there's some conditions about this equilibrium is that it depends on two things. It depends on how fast the dark matter is being captured. That depends on how strongly it's coupled to normal matter, especially the quarks. And then it depends on another thing, which is independent, is how fast it annihilates. So the dark matter has been being trapped in the sun for long enough to build up enough density for the annihilation to happen. And the annihilation also has to happen fast enough so that it will reach equilibrium. And this time scale, if you compare with the lifetime of the sun, and if the age of the sun is greater than the time scale required to build up an equilibrium, then you can simply say, okay, the annihilation is at the equilibrium, and the rate you get is simply 1/2 of the capture rate, which only depend on the cross-section of the dark matter scattering of protons and neutrons, which can be directly correlated with direct detections at the terrestrial experiments like Gamma and Xenon, CDMS. And this is some early study we did for the propagating these neutrinos out from the sun, which is actually a quite complicated situation because of two things. There's oscillation, and there's a very high density of material at the sun, so the neutrinos can actually hit resonances in there on its way out. And there's some other effects like absorption or scattering, and that could be even something more complex like a tau regeneration, which means a new tau scatter with charge current interaction going into a tau, and tau decay back to a neutrino. So that's, and we develop a code that does this. But all this effort is actually quite meaningful because what can be seen is that if your injection spectrum, injection by meaning your dark matter annihilate, and that may have some features in the energy spectrum in neutrinos which started at the sun, the center of the sun. And even after all this process of propagating, you can still maintain some of the features. And if you have a bump at the high end, you can probably still see it at the Earth. So that.
Sorry, I walked in a couple minutes late. What mass dark matter are you thinking about?
We're thinking about the generic weak scale masses. Because if you want to look at neutrinos, the only experiment that does it now is the IceCube. And IceCube has a 10 GeV threshold for the small part of it, and for the bulk part of IceCube has a threshold about 60 GeV. So anything has to be above that in order to be seen.
All right, so you're looking for ballpark 100 GeV neutrinos that are coming out of the sun.
Yes.
And would be, all right, so you could see them with IceCube, probably not much else, and they would be pointing from the sun.
Yes, you have to track around the sun and see if there's an access in the energy window you expect, which is for 100 GeV dark matter could be anywhere between the 70 up to 100.
Did you show, I don't know enough about neutrino physics from the sun. Is it just falling exponentially from the thermal?
That's actually a good question. The background from atmosphere is falling like a power law in the detector. But for this dark matter, because we have a fixed energy to start with, it's the mass of dark matter. So if you go through some channels like nu, which is the perfect channel, it's a delta function here. You won't see a delta function at the Earth because of propagation, but you can still have quite a big bump here. And that's actually scenario is actually not allowed in many of the models, but you can have, say, WW or ZZ or going into quarks. And if you go to hadronic final state, it's going to be a falling curve. That's not very good for discovery, but WW and ZZ, because spin correlation, we're going to have a bump at the endpoint. So that bump really helps getting this.
Where's the WW coming from?
You have, say, for example, we know dark matter pair annihilate into W plus W minus.
Oh, because you're favored to go to the charge for the heavier
That's
stuff?
the one of favorite channel for us.
All right, okay, so if it's pure neutrino, then you should see a line, but if you go WW, then you're gonna go decays, and, okay, got it.
So this is what we did. we have neutrino, we have codes for the propagation, which is on this part, has the full propagation effects. And we also take account of the spin correlation that give you particular features in the neutrino energy spectrum. And for that one, sometimes it's necessary because if we're talking about 100 GeV dark matter, and if we talk about annihilation final state into quark pairs, then the bulk part of your signal is going to be fall below that threshold that you are never able to detect them. But if it's WWS, and it is very important to find out how much of the high energy part that is actually above your threshold, so you can get a more accurate estimate of how much you see. And this is not as sensitive. We are talking about TeV and even higher masses because it's way up compared to the threshold. But for weak scale dark matter, this is actually quite important.
And where does, on your previous plot, where does the atmospheric neutrino background, what does it look
Actually,
like?
I didn't show the neutrino background here, but we're going to see in a table. I have a table. I probably have a table in the backup slide. So this is the most up-to-date constraint from the ice cube. And for them, they usually show two channels, the WW channel or the BB channel. I think the BB channel, what they call the soft channel, because it's, the neutrino is coming from the shower, usually from the hadrons. And the WW is they directly decay into neutrino, and that channel, neutrino can come out and actually quite energetic. So this band is the WW, and for the spin-dependent cross scattering constraint is actually better than the direct detection experiments. And this one is from the BB final state. And what we did in one of the papers is we want to look at this situation and say we want to go away from the most studied cases of the WWB and then some other channels like the and we'll say, okay, so the most optimal scenario for ice cube is you have a line spectrum at the mass of the WEM. So the dark matter goes to the bar. But it will not happen if your dark matter is Mariano fermion and has only left or right-handed coupling to the fermionic current. Then your cross-section, if you calculate it, which has been known for some time, is suppressed by the mass of your final state fermion. So if it's a neutrino, the term is 0. And if you look at the P-wave annihilation cross-sections, it's dependent on V squared. So, and we know at the center of the sun, the velocity is almost 0. So this is also very suppressed. And however, it doesn't mean that they can't go into a neutral bar. The way you can do it is your the final state has some actual vector boson like the Z, or maybe if we're talking about charged particles, you can have a gamma, or if you're a quarks, this could be a gluon. So this will flip the spin of one of your final state fermions. So it will lift this type of suppression into something like this. You still have these velocities, which is for the P wave, but for the S wave, there's 1 over r to the 4th, and this r is the ratio of, if I'm talking about the T-channel process, is the heavy particle that runs in as a mediator there, and it's a square of the mass ratio between that mediator and the dark matter. So if you think about some processor like this, for example, so this mediator, we'll call that eta or something else. And this is dark matter, and this for lepton and lepton plus. This could be some lepton partner. And the S wave for a process with actual radiation, let's call that gamma, has a non-suppressed part that is dependent on the mass ratio. So if your intermediate mass is not that different from your WEMC, then this is actually a fairly large annihilation cross-section. So it allows your dark matter to go into the bar plus something else. And what is even better is if you work out the energy spectrum of the fermions, which means either charged particles or the neutrinos, they, of course, it depend on the mass of the mediator, depend on the mass of the boson irradiated, and the mass of the dark matter. But in general, they have a very large peak-like structure or a very large bond at the endpoint. So this will make this channel looks almost the same as a neutral bar because the majority of your final state particles actually have high energy. And this is actually a good channel for dark matter search.
So this is really dependent on whether there is in fact another mediator.
Yes, it
So
is.
there has to be one.
It has to be one. And actually there's the collaborators, Y.E. Kuhn has a paper, actually I was also part of it. And if I talk about Mariana fermion neutrino, it goes through a vector or a scalar as well as a T-channel and S channel. And then all these diagrams, the energy spectrum look like the same. So you can actually use some effect operator way to get to this. Guarantee that there's some high energy particle that make this happen.
So the final rate could actually be fairly high if this were true.
The final rate, you mean the annihilation cross section?
The flux at the Earth.
Flux at the Earth depends on, it doesn't really depend on how fast annihilate, as long as there's equilibrium. It actually depends on how strongly they couple to, say, other particles. And it only depends on how fast these particles are being captured gravitationally at the sun. So at this point, they will assuming that these particles are being gravitationally captured at the sun, and there is an equilibrium. So, and this is some assumption that we can discuss later, but yes, this is something that doesn't really depend on. It's highly model dependent, I would say. It's highly model dependent, and here we're just trying to give a phenomenological and constraint that you will see later that we do all the channels, and if your theory actually predicts a certain branching into these channels, you can just use these results and give the bound on your theory.
The shape doesn't depend on whether it's equilibrium or not, but it's the normalization.
It's a normalization depends on whether they're equilibrium or not. That's right.
All right, can I ask another dumb question? If I think about the ratio of the mass of the Earth to the mass of the Sun,
Yes.
it's very tiny.
Yes.
But the flux at the surface of the Earth, the distance from the center of the Earth to the surface of the Earth, is very small
Yes.
compared to the center of the Sun to the surface of the Earth. Could you be seeing these from
That's a
a
good
annihilation
question.
in the center of the
Very
Earth?
good question, because when people started doing those studies, look at the Sun, they also calculate for the Earth. But what happened for the Earth is because the gravitational well is much shallower for the Earth, so it's more difficult for the particle to be trapped.
But no, I don't think that's what he's saying. Yeah, it is more difficult, but you write it in the Earth, so it should be easier. But the background is going to kill it, because when you look at the Sun, you can see the source and not the source. But on the Earth, you don't have a control over the background.
And
It's all hidden.
actually, I diverge on that. We can talk about it
Because,
later.
I mean,
Because they
it's
share the
similar.
same
It's got to come
background.
from the center, though, because that's where the density is going to be the highest. I mean, it's true.
And you're right in the center. I mean, essentially,
And
when you run an experiment.
as
All
far
right, you know,
remember-
you should give your talk. I'm sorry.
As far as remember, for the Earth, you can do the same, but the signal flux is actually smaller compared to the Sun.
Even with the ratio of the distances.
Even with the ratio distances, but it's more or less because of the Earth's gravitational well is much shallower, and so the capture rate is much lower.
Yeah, got to go over the density of the ratio of the densities versus the ratio.
So here's a list of
Yeah,
these
that's-
annihilation channels that is relevant for this vector boson radiation. Here I only listed the final state, especially with the taus, because if you go to the electrons and muons, they will very quickly be absorbed inside the sun. And the tau has such a short lifetime, so it can decay before it's getting absorbed. And this will be the only electron channel final state that is inside the sun medium. And for, I would say for all these channels, the direct detection bounds is going to be, say, rather weak, depending on whether they're coupled to other particles or not. But one of them, if they couple to electrons, there is a relatively weak constraint on direct detection that you can use electrons inside of the detector to put a bound. That is, I think, it's probably 1 or 2 orders of magnitude compared to the coupling difference. And here, this is the mass dependence on the spectrum. The point is that as a relatively high masses compared to the boson radiator, is approaching this spectrum. That is a peak at the very end point that is almost the same as the monochromatic neutrinos. However, at the lower masses, if the dark matter mass is become comparable to that of the gauge boson radiated, then you have to start counting in those virtual vector boson contributions. That could significantly change the shape of the spectrum. And the blue one is what happens if you have the virtual contributions. And this panel shows the injection spectrum for different channels. And the take-home message is if you radiate some boson that directly decay into a neutrinos like the Z or the W, it could have a large peak at the end. Otherwise, the lepton decay, or from the shower or any other place, they're going to get a falling spectrum like this, or like this. And for these channels, you really have to have a relatively large mass in order to have a significant part of the spectrum above the threshold. So this is another case at 1 TeV. The previous one is at 100 GeV for the dark matter mass. You can see the shape is getting closer to the photon case where the peak is getting sharp at the end. So you put this signal and assume there's an equilibrium or not. That depends on how much you want to scale it. And for the ice cube, and there are 3 discovery modes. You can calculate what they call the pure Gaussian bands, the contained event, and also the small part of the ice cube called deep core. I'm not even going to get into the details of how to calculate those different types. But these are 3 sets of events that is detected. And for each set, you can put a bound on how much signal you get, and the signal will eventually translate into the capture rate, which depends on the scattering cross-section of the dark matter to the protons and neutrons inside the sun. And so these plots you can compare with the xenon and the CDMS constrained plots. And you can find actually some of them are pretty powerful. And this is assuming about a 1 full year 1 kilometer cube ice cube. So that is in the full flashed mode. And for ice cube itself, because of the threshold, it's more sensitive to masses above 100 GeV. And with a little deep core inside where it has a denser strength and a smaller threshold, it's more sensitive to dark matter masses below 100 GeV. And you can put the 3 categories together. So for each of the channels, you can get some combined constraint on how big the cross-section will be for scattering. And a final slide. This is what's really called a combination between the channels, because we're talking about just annihilation channels. We're not talking about the theory, which is theory that gives those channels. And if you come up with yours to see the scenario or some other model that will have significant branches into, say, a few of these channels, then this is how you combine these results into a single bound on your theory. And these sigmas are the sigmas of channel J from the set of experiments at the events data I. The I could be the ice cube or deep core. And this n is the tag for how many n sigma significance you have for your constraint. And those boost factors will be given by your theory. And in some cases, especially at a relatively low mass or high mass, the constraint will be dominated by one of these events, one of the categories. Then you don't have a sum over the different sets. It's become a very simple event formula that you can just take in your branching ratios into each channel and get what is combined constraint on your theory. Of course, theory means that you have to check other things, like there's equilibrium, and whether it's actually get captured or not, which we don't really focus at this point. Okay, so let me change gears. So instead of the sun, we can look at another mode for indirect searches of dark matter. And for the sun, it was dark matter annihilation. And you can also look at the dark matter and some other particle scattering. And usually this picture comes to your mind. That is the which have a lot of very strong local expertise in CDMS and some other experiments. And actually, I'm very interested to know if there's kind of updates about certain results. But I'm not going to talk about this low energy scattering at this point. I'm thinking about scattering process that is happening inside deep in the universe where there's energetic particles flowing around, like electrons or protons from a jet inside a nuclear, active galactic nuclei. And those particles, so if your theory has a partner to the electron or the quark, it is possible that this dark matter and the particle go through an S-channel resonance. So this, if the energies are right, if the energy is right, then you can go through this S-channel resonance, and this will be a cross-section many times greater than what you can get at the rather small energies. And what we see, we can't see the scattering, but we can see the gamuts from it. So this is what we can see. And those previous works are focused on the scattering of the dark matter to not protons but electrons, and where you can do the parton level calculation and calculate how much gamuts you get. I'm going to very quickly go through them. So this is the favorite place to look at is Centaurus A. It has, we know there are jets, there's a lot of radiation activity going on there.
So you're thinking about the jet coming from the AGN and,
Yes.
and just the dark matter particle that's part of the galactic structure. So you're
Yes.
assuming that the dark matter is not coming in.
I'm assuming
That it's
dark
not
matter-
part of the jet.
It's
just
not part of the jet. The
part of the
jet is
halo.
just the star-model particles, the proton electrons. Then when it's shooting out,
So it's almost like a
it-
fixed target experiment.
Yes, it's a fixed dark matter.
Right. The dark matter is essentially a fixed target.
That's right. And why interesting this is because there's sometime earlier, when Fermi was looking at this Centaurus A, there seems to be some kind of structure in the data points. And you may imagine that, and also this one is Marquez. You may imagine maybe there's something going on like this, or maybe this is a little bump. Well, the data come and data go, but who knows? We can play with this possibility. And these are the diagrams that are involved in this scattering. On the left side is a proton and dark matter scattering, this S-channel resonance. And here is only one of the protons that are participating in the process. In case of electrons, you really get the photon from anywhere inside of a diagram. For the S channel, it has to be a charged partner to the electron, so it will also radiate. This is what we call the internal ground shot, which is also important. And one important point is you need to estimate how much dark matter could be around the galactic center. And this is I quoted from Stanford performance paper that you can look at the gondola silk study, and this is pure astrophysics. It depends on the amount of dark matter flowing around the galaxy center depends on the mass of dark matter, of course, of us annihilate, and also the time of the black hole in the center. And I can't say I really understand the formula, but I'll answer some people in the audience that have a better understanding for why it's like so. But what you at the end of the time is you can expect there's a fair amount of dark matter that should be around in such a big galactic center, and then you can use that as a target for all the cosmic rays. And you calculate this scattering process, and the feature is very striking because you almost always get resonances in the cross sections, and the reason is there's two places to get resonances. When you can call the sum of the momentum in the initial state to be the S, or you can call this sum of the final state momentum to be the S prime. So either this S or the S prime are on shell, which means the mediator, the partner to that electron is on shell, and it could give you one of these peaks. And however, there's one thing that's also interesting is in order to get the primary resonance, this is the sum of the initial momentum on shell, and you can't have gamma rays that is more energetic than the mass gap between the electron partner and the dark matter, because in that case, it just doesn't add up. So this will give you an indication of where to look for signals. Suppose you have 100 GeV dark matter, 120 GeV partner. And then the gammas will be somewhere below 20. Okay. And this is what you get. If you integrate all this contribution from inside the cosmic ray inside the jet and the cross section, and you see there is a drop. And this drop is exactly where the mass gap is. And so people play around it. And I stole a picture from some people at Argonne, I think. And they have a actual dimension model, and their KK dark matter is giving the right level of the signal that can explain the points, data points from Fermi at this entire setting. And at the same time, their annihilation is not giving as much signal, which is a good part, but I don't understand how they get that, because their model doesn't seem to have a suppression on annihilations. But what I'm saying is this is not a story, because all these part of the studies they are doing electron scattering. We want to do protons for a few reasons. Because for one, when you do the electron dark matter scattering plus actual radiation in the final state, you'll have a next to leading order cross section to begin with. And the good way is to do the inclusive calculations. And you can, for example, you can use other ways, a more phenomenological way to estimate how much radiation you can get from electrons. It doesn't just has to be one. And for protons, there's other good parts. Is because we know for protons there's a PDF, which electron doesn't. And the PDF will guarantee that you always have the proton that has exactly the right energy to put this S channel on resonance. Because the particles can come in at a very high energy. And so if you need 20 GeV to put it on resonance, and your proton is 100 GeV in this coming energy, then the PDF will just pick up that 0.2 to make the energy right for the resonance. So this means for protons, if you have energy above that threshold, you always have a resonance. And another reason is for protons, the photon doesn't have to be a hard Bremsstrahlung from the charged particle. You could have that quark shooting at you. So any photons coming from the showering of that quark can be a signal. And in this case, the cross-section will be much greater because you don't have suppression from a large angle radiation scattering, which will tend to suppress your cross-section if you have large angle and energetic photons. And if you're lucky enough to have some protons that leak out from the jet and directly shoot at you, and then you're going to have a huge enhancement from those forward region photons, which could coming from either initial state radiation or remnants. And these particles are very energetic because they carry the most of the energy of the coming cosmic ray. And the hard scattering only happens at a fixed energy. For example, you can think about 10 GeV cosmic ray, and it will only deposit about a few 10 GeV into the hard event. But the rest is in the remnants, and they will also radiate. Okay, but there is a drawback point. Is we'll talk about the scattering between these protons and the dark matter. These couplings will directly bring you to direct attention. So you have to do the constraint on it and see how big the coupling is allowed by satisfying this Zeno or setting mass constraints. So this is a part to show the comparison between the proton scattering and the electron scattering. For electron scattering, most of the events happen at the resonance energy, where it's comparable to the mass gap. And this is at the parton level. And if you do the parton level calculation for protons, it's going to be here. You do have a feature that is a PDF will put this cross-section on shell at some point, which is above the mass gap. And however, if you just do the parton level, you'll see the cross-section is much lower. One from the suppression of PDF, the other is the quark has a fractional charge. And it also, this will be, it also depends on your theory's coupling between the dark matter and the parton. So there could be some differences. However, if you do the inclusive cross-section, you see that this is much greater by somewhere between 1 or 2 orders of magnitude to the next leading order cross-section. And plus, we know for inclusive event, there's going to be some 20, 30 radiations in the final state instead of just one, which you have on the fixed order calculation side. So we handpicked most lucky Lagrangian for a few purposes. For one, this is to make our signal rate large for the resonance scattering. For the other one is it will suppress annihilation because exactly the same reason that it's going to be P-wave suppressed. And the third is that we put it on the right-handed permanent currents so that you don't automatically couple to the down-type torque. That is help a little bit on the direct detection constraints. So this is just a recast from a slide earlier that this type of Lagrangian will give you P-wave suppression. So your annihilation will be, your leading annihilation will be a three-body annihilation, which we checked that radiating actual gluon will not give you enough antiproton to be in conflict with the epimella. And the radiation in gammas, which is actually the signal, is not actually good enough for our galaxy. So this AGN is probably a leading case if you want to look at this type of interactions. For direct detection constraint, we reconstructed the xenons constraint. At that time, we didn't know about the CDMS, but we'll explain very shortly why the CDMS silicon results actually is not very good for us actually. So we calculated what is the scattering cross-section with nucleons for our theory, which is where the leading contribution of the twist-2 operator, which is done by some other papers work beside it. And we included both the spin-dependent and spin-independent contributions, and we found that at a few hundred GeV of our dark matter, the mass gap is necessary to be above almost 100 GeV for our case. And our coupling is actually pretty big. We choose the coupling to be 1. This to get an estimate of how big it can get. And at this point, so if you look at what happens at a small mass, for example, 7 GeV here, or 8 GeV here, we know that CDMS constraint is not as strong as xenon, if you want to consider that to be a signal. So everything will scale down, but the structure will remain the same. So what we expect is there is a mass gap at the low mass of the dark matter is going to be greater than the mass of dark matter itself. So that is actually not very good for us because the resonance energy is where you start to get contribution from scattering, and it's dependent on the mass square differences between the square mass, the partner mass and the dark matter. So at small masses, this become have a quadratic dependence on the mass differences. So this will make a very high energy to start with, which is actually not very good for us. And so then you look at the way you calculate how much flux you get there together. And the only thing I want to point out is here is we don't assume that all the protons are along with the jet axis. So you could have protons shooting at with some angle from the jet axis. And in that case, we have to simulate what is differential spectrum, differential in terms of the angle and the energy on all directions, which is quite computation intensive. And we did it with the Sherpa, and there are two kind of radiation you get from the proton case. One is mainly from the radiation or the showering in the final state. And those photons are very easily get to large scattering angles, but they are not very energetic. They are capped by the mass difference between the partner and the dark matter. And the other type of radiation is that is coming from the inner state. So it could be ISR, or it could be the radiation from the hydrogenization of the underlying events. And those could be much more energetic than any of these particles that are involved in the process. So this is a table that categorizes. And the first category, this is what we call the final state, the radiations. They are present in all jets because they're coming from they're just coming from the protons that is shooting exactly along the direction of the jet axis. And it depends on what your jet looks like. You may get the radiation in the forward region, or you may not. That depends on astrophysics. And this is a plot to show how much enhancement you get in the forward region that from inclusive calculation. what is interesting is for the electron case, the initial state radiation also become much more important. They are talking about high energy radiations, which is actually what we expect from looking at the diagrams in the previous slides. And you can also see what is the enhancement between the inclusive and the parallel level calculation.
So you're trying to pick this out of a signal where you're directly looking into the jet.
We don't, because the jet is at some angle to us. And then you're looking at photons that shoot off from the jet. Because when the jet hits something, it can radiate
I thought
radiation.
what you were just showing was the stuff in the forward direction with the jet.
This part is only if there are some particles, say some proton inside the jet is not exactly along the jet axis.
Okay.
So it could have some small angle, say, towards us. Then you can see some.
Oh, okay, so you're hoping that the high one comes in
the
at
jet is
some
kind of
funny.
fluffy shape instead of very collimated. And this is question is how many protons inside jet actually point towards us instead of just along with the jet axis. So this depends on what is how boosted the frame of the protons are. We assume that the proton is also isotropic in some frame that has a boost in comparison with the central black hole. So if we assume that boost to be the same as that of the electrons, which I know is about a factor of 3, and then the Lorentz boost will give you a phase-space expression about the torus and magnitude, and that is actually can be compensated by the very high, much higher intensity in the forward region. But if you have a much greater boost, for example 10 or even higher, and everything is collimated, then you don't get the same thing of this. All right, this is a contour to show the two contributions. The central region is where the forward radiance dominates. This angle is the direction of the proton from the jet axis. And the right edge is the contribution from the collimated protons. So at the low energies, we know that this part, most of the gases from here are below the mass difference. So at the low energies, you get a lot of these photons. But if you go higher up, they become much smaller, and the initial state radiation actually dominates. But that really depends on how much protons you can actually get in that direction. And this is the total results. We have two of our simple points. One has a dark matter mass at 300, and one is 1 TeV. And the black curve is showing that we have a boost factor of 3 for the frame of the protons, where you get a high energy tail coming from the initial state and the remnants. And the orange curve is a case where all the protons are collimated along the jet axis, and you don't see anything from those energetic you don't see any of the energetic radiations. And in comparison, these blue curves are parton level calculation results. And this justifies our work. Is actually saving our scenario from being dismissed as not optimistic. So, just a few tips for model builders. So the signal depends on coupling square, and the constraint from direct detection depends on coupling to port. And however, their dependence on the mass difference is quite complicated, and because for the AGN case, that is the starting point of where you start integrating out the contribution from the incoming flux. And for the direct detections, that gives you the suppression on the cross-section of the scatter. And that's, there's no single very handy formula you can do that. You can estimate that and do the real calculation. And, well, let's see. Yes, if we want to do a large dark matter, the mediator, that is the charged particle to the lepton or the quark, also has to be light. Otherwise, you are not going to see anything. Okay, so how much time do I have?
Maybe 5 to 10 minutes.
That's enough. So just a few comments of what happens in our galaxy. And same thing can happen in our galaxy, right? We expect that. But if you actually look at what is the proton flux inside our galaxy, this is actually quite accurately known. And there are two reasons why I don't see them. For one, which is the lesser evil of the two, is we have a diffuse protons inside our galaxy. It goes in all directions. So you start to see this forward radiant photon in all directions, which is a good thing for your signal level. But it's a bad thing for the shape, because the shape will just follow what the incoming flux is. And you have a parallel flux, and the signal becomes parallel. And that's very bad for picking up the signal. In comparison, that if you do the particle level calculation, we only take care of the hard radiations in large angles, but not the forward region. This can still expect some features, but this is not there if you do the inclusive calculation. But this is not the most important thing, that's why we don't see them. The real reason is we don't have enough cosmic reflux in our galaxy. And so this is, we checked with the Gopher models, which have this plot to show the distribution of the cosmic protons, say, above some threshold energy, versus where it is. And this distance is away from a galactic disk. And you see a very nice, almost linear dependence. And then we choose two Fermi windows, which one is in a more central region, and the other is actually some distance from the disk. And if you do the calculations, you find something like this. This is the signal from the scattering. This is a diffuse background. And why this is so low is because our galaxy doesn't have a jet. And this is some mathematical tricks you can play about annihilation rates and the scattering rates. So annihilation rate is something of quick scale cross-section times incoming flux. And this flux, in case of annihilation, just spell off time, light times the dark matter density. And so this is all the density of dark matter in annihilation case contribute. But in case of scattering, and you can do the same trick by writing your source into something like a flux. You find that you are only integrating out the part on the tail, that your particle has to be above some threshold. And for that one, it's very tiny nowadays. So there's almost, some 8 orders of magnitude suppression, and there's no hope for our galaxy. And there's a sub-summary, and we found that particle level calculation from protons is probably not good enough. You have to do the inclusive full calculation. And this calculation and radiation. And let's see. And we found that the proton signal is actually not very suppressed in comparison with the electron scattering case. So this would be a nice that ideal model coupled to electrons or neutrinos or quarks can actually enjoy this this AGNs to be a source for a potential signal. And we certainly call for more detection-friendly models. I think this is the end. And backups. Thanks.
So questions?
So what have you mostly been thinking about SUSY type models for your mediators, or do you have others in mind that you're really thinking about?
The one we chose actually is very similar to SUSY. We didn't actually say SUSY because one of our purpose to start is we want to see if you choose the most optimistic Lagrangian and what is the highest amount of signal you can get. And only with this one you can start talking about some other theories which usually you expect to be last way. And what we see is we're getting a signal level that is becoming visible. But although a little bit larger, it has hope of being and so for SUSY, you can very easily make it. The thing is, you can, for example, for SUSY, you can call that mediator a squark, say a scalar quark, and then it should do it.
SUSY makes it easy because in some sense you can get whatever couplings you want and turn them. Would charge takes do it?
Charge.
Here, so that way you can get a charge thing in the middle, or is it?
Oh, I don't understand your question.
I'm trying to think about how to couple to the leptons somehow to get the
A
charge.
couple of leptons. I think for SUSY it's easier to couple, of course.
Yeah, okay. That works. How much would your answers change if these were axion type things instead of electron coupling?
Well, haven't thought of that. The Axions. Well, this signal really depends a lot about how big your company is. And for Axions, you have to look at what the maximum allowed coupling you have. And also, look at S channel. Look at S channel resonance for piece of Axions.
All right, so if I go the other way, and I say if dark matter is sort of an electroweak coupling type thing, if there is no light-ish mediators, you can't play this game at all.
First, you need a mediator for that channel resonance. And second is you need a mediator mass not too different from your wind. Otherwise, this...
So if it's all high scale,
if it is very high scale, then the threshold energy will kill you. Other questions?
If not, let's thank you again. Thank you very much.